Hi everyone, I am K. Swarna Devi, Assistant Professor, Department of Mathematics, otherwise known as Pioneer Meenakshi Women's College, Pulvanthi. This is a learning resource for real analysis. In the last video, we have learnt some of the theorems in countable sets. In this resource, we are going to see some more problems in countable sets and uncountable sets and Holder's and Minkowski's inequality. So this is one of the problems by using countable sets. Any countably infinite set is equivalent to a proper subset of itself. Before going into the problem, let us recall the definitions. Two sets A and B are said to be equivalent sets if there is a bijection between them. A set is said to be countably infinite if there exists a bijection from the set to the set of all natural numbers. And a set is said to be countable if it is either finite or countably infinite. Using these three definitions, we are going to see the problems. I am repeating the problem. Any countably infinite set is equivalent to a proper subset of itself. So I have to take a countably infinite set and I have to prove there is a bijection from that set to its proper subset. So for that purpose, I am taking the set A as countably infinite set. Since it is countably infinite, we can list the elements of A as A1, A2, etc. I have to take a proper subset of A, so I am leaving the element A1 and form the set B as A2, A3, etc., An, etc. Then what will happen? B is a proper subset of A. So I have to prove that this A and B are equivalent. So I am forming the map F from A to B by f of an equal to an plus 1. So what is the image for the element a1? Yes, it is the element a2. So for the element a2, the image is a3. Likewise, we are defining the map f. So I am going to prove this f is a bijection. First of all, I am going to prove this f is 1, 1. So if the images are same, then the elements are same. I am taking f of a1 equal to f of a2. Sorry, f of an1 equal to f of an2. What will happen? an1 plus 1 equal to an2 plus 1, which implies n1 equal to n2, which implies an1 equal to an2. So I am having f is 1, 1. Then I have to prove f is onto. So for onto, I have to start with an element in codomain and I have to find a pre-image in domain. For every a n plus 1 belongs to B, there exists an element a n belongs to A such that f of a n equal to a n plus 1. So for every element of B, there exists at least one pre-image in A. So what? F is onto. So we are proving f is 1, 1 and f is onto, and hence f is a bijection. So since f is a bijection, we can say that the sets A and B are equivalent. So what we have proved that we are taking a countably infinite set and we have proved that the set is equivalent to a proper subset of itself. Now let us move to the second problem. Any infinite set contains a countably infinite subset. So I have to take an infinite set and I have to prove that there is a countably infinite subset within the set. For that purpose, I am taking A to be an infinite set. What I have to do? I have to find a countably infinite subset B and I have to prove that this B is a subset of A. So for that I am taking the first element A1 belongs to A. So since A is infinite, it has so many elements. So I can find one more element A2 in A which is not equal to the previous element A1. So since A is infinite, we can choose another element A2 belongs to A minus singleton A1. So proceeding like this, we can select the next element A3, A4, etc. So in a particular case, in a particular stage, we have already chosen AN. So suppose we have chosen A1, A2, etc. AN from A, then we are in the stage to select the next element AN plus 1. So since A is infinite, the set A minus set of all A1, A2, etc. AN is also infinite. If you remove some of the elements from an infinite set, the resulting set is also infinite. So A minus set of all A1, A2, etc. AN is also infinite. So I can find an element AN plus 1 belongs to this set, which is not equal to the previously selected elements. So I can find the set B, which is A1, A2, etc., AN plus 1, etc. So where are the elements of B can be taken? Yes, they are taken from the set A. So B is a subset of A. Since the elements of B are listed as A1, A2, etc., AN, etc., this B is countably infinite. So we are satisfying our statement, any infinite set contains a countably infinite subset. So using this problem, we are going to prove the next problem. Any infinite set is equivalent to a proper subset of itself. So I have to take an infinite set and I have to prove that this infinite set is equivalent to its proper subset. So for this purpose, I am taking A to be an infinite set. So what will happen? By using the above problem, I can find a countably infinite subset B. That is B equal to A1, A2, etc., AN, etc. Then using the set theoretical notation, I can write A equal to A minus B union B. Then if I am considering the set C, which is a subset of A, as C equal to A minus B union A2, A3, etc. That is, I have to delete the elements of B from A and I have to join the elements A2, A3, etc. Then what will happen? From A, I am deleting only the first element A1. So what is my C? C equal to A minus singleton A1. So I am deleting one element from A. So I am having C as the proper subset of A. So now I am having a proper subset, that is C. What I have to prove? This A is equivalent to this proper subset C. So I am defining the function f from A to C as f of x equal to x if x belongs to A minus B. Because C is categorized as A minus B union set of all A2, A3, etc. So if I am taking an element from A minus B, then that image of the element is itself. And if I am taking the element from A2, A3, etc., means the image of the element is the next element. That is f of AN equal to AN plus 1. Then if I am, by selecting this type of f, we can easily prove that f is a bijection. That is, for different images are having different elements are having different images, and for every element in the codomain there is at least one pre-image. So f is a bijection. Since f is from A to C is a bijection, we can say that A is equivalent to C. Next, we are moving to the concept uncountable sets. So what do you mean by uncountable set? Yes, it is a set which is not countable. So the sets which are not countable are termed as uncountable sets. So we are proving the following theorem 1.8. Open closed interval 0, 1 is uncountable. So we are going to prove that the open closed 0, 1 is uncountable. That is, the set is not countable. So definitely we know that the set is not finite. So we are going to prove that this set is not countably infinite. So that we can prove that this is uncountable. So we are starting with an element. Every real number in open closed interval 0, 1 can be uniquely written as a non-terminating decimal. So if I am taking any element from 0, 1, the interval 0, 1, it is of the form 0 point something, or it is the element 1. If I am taking the element 1, then that 1 can be written as 0.9999 etc. If I am taking the element 0.54 or 0.45, if it is a terminating decimal, then I can make this terminating decimal as non-terminating decimal. How? If I am taking 0.54, I can write this as 0.539999 etc. So every terminating decimal can be converted into a non-terminating decimal. So if I am taking 0.A1, A2 etc. an, where 0 less than or equal to a less than or equal to 9, then I can write this number as 0.A1, A2 etc. an 000 etc. Suppose I am assuming the open closed interval 0, 1 as countable. I am going to prove this is uncountable, but we are assuming the contradiction 0, 1 is countable. We have to arrive at a contradiction. So since I have assumed that 0, 1 is countable, I can say that 0, 1 is countably infinite. So I can list the elements of 0, 1 as x1, x2, etc. Where is this x1 is from? This x1 is an element of 0, 1. So it is of the form 0 point something. So x1 is 0.A11, A12, etc. x2 is 0.A21, A22, etc. Similarly, we can define xn as 0.an1, an2, etc. So, beyond these elements, I have to find a new element in order to bring the contradiction. So, what I am doing is, for every positive integer n, I am choosing an integer bn such that bn lies between 0 and 9, and bn is not equal to 0, and bn is not equal to ann, that is the diagonal element of each x1, x2, etc. So I am taking the element y as 0.b1, b2, b3, etc. Then y belongs to open closed interval 0, 1. Y 0, because y is of the form 0 point something. So the decimal part b1, b2, b3 are all not equal to 0, are all not equal to ann. So each bi is different from each aii. So this y is different from each xi in at least in the diagonal place, that is at least in the ith place. So this y is not equal to xi for each I. So we arrive at a contradiction, and hence we are proving that open closed 0, 1 is uncountable. So we have to see three corollary of this theorem. The first corollary is any subset A of R, the set of all real numbers, which contains open closed interval 0, 1 is uncountable. So if I am taking any subset of R, if that subset contains this 0, 1 as a subset, then I can readily say that that subset is uncountable. So let us see the proof. Suppose I am taking A, which is countable. Then by using the first theorem in the previous video, what we are getting, any subset of a countable set is countable. So any subset of A is countable. So open close 0, 1 is also countable, which is a contradiction. Now only we see that this is uncountable, and hence this A is uncountable. And let's corollary 2, R is uncountable. So in the previous corollary, instead of A, if we are taking the set R, then automatically we arrive at the result R is uncountable. And in corollary 3, we say that the set of all irrational numbers is also uncountable. Remember, we have seen that the set of all rational numbers is countable. But here the set of all irrational numbers is uncountable. So suppose I am taking the set of all irrational numbers S is countable. Then already we know that Q is countable. If you take union of rationals and irrationals, we are getting the set of all real numbers. So S union Q is R. R is countable. We are arriving at a result, that is R is countable, which is a contradiction. So why this contradiction happens? since we are assuming that the set of all irrational numbers is uncountable. So what we conclude that is the set of all irrational numbers is uncountable. So now let us move to this next section, Holder's and Minkowski's inequality. So this is the statement for Holder's inequality. If P greater than 1 and Q is such that 1 by P plus 1 by Q equal to 1. So we can take any number Q such that 1 by P plus 1 by Q must satisfy the equation which gives the result 1. Then the inequality is summation I equal to 1 to n modulus of ai bi less than or equal to summation I equal to 1 to n mod ai power p the whole power 1 by p into summation I equal to 1 to n mod bi power q the whole power 1 by q. What are all the elements a1, a2, etc.? Yes, they are the real numbers. ai's are real numbers and bi's are also real numbers. Now let us see the proof for this Holder's inequality. Before proving the result, we are proving this inequality. X power 1 by p, y power 1 by q less than or equal to x by p plus y by q, where x is a positive number and y is a positive number. And if either x or y equal to 0, then the result is trivial. So we are assuming that x and y must be greater than 0. We are considering the function f of t equal to t power lambda minus lambda t plus lambda minus 1. What is my lambda? Lambda is 1 by p and t is a positive number, t greater than or equal to 0. So we are going to find the derivative of this f of t. F dash of t equal to lambda into t power lambda minus 1 minus lambda. If we take lambda common, then lambda into t power lambda minus 1 minus 1. What is f of 1? If you put t equal to 1 in f of t, we are getting f of 1 as 0 and f dash of 1 as 0. And also we know that f dash of t is positive for 0 less than t less than 1. If you put any value of t between 0 and 1, then f dash of t will yield a positive answer and it will yield a negative answer if t is greater than 1. So using these results, we conclude that f of t is less than or equal to 0 for all t greater than or equal to 0. For all positive t, we are getting the value of the function as negative. So in particular, if we are putting x by y instead of t, we get f of x by y less than or equal to 0. So we are substituting this x by y in the equation of f of t. And we are getting x by y power lambda minus lambda into x by y plus lambda minus 1 less than or equal to 0. If I substitute the value for lambda as 1 by p, I am getting x by y the whole power 1 by p minus 1 by p into x by y plus 1 by p minus 1 less than or equal to 0. We are multiplying by y. We get x power 1 by p into y power 1 minus 1 by p minus x by p minus of 1 minus 1 by p into y less than or equal to 0. Using the result 1 by p plus 1 by q equal to 1, we are arriving the result x power 1 by p, y power 1 by q less than or equal to x by p plus y by q. Now let us come to the main part of Holder's inequality. We apply the above inequality to the numbers. So instead of x, we are taking xj equal to modulus of aj power p by summation I equal to 1 to n mod ai power p. And instead of y, we are getting yj equal to modulus of bj power q by summation I equal to 1 to n mod bi power q, for each j equal to 1 to etc. n. So if we apply the values of xj and yj in the previous result, we are arriving mod aj into mod bj by summation I equal to 1 to n mod ai power p the whole power 1 by p into summation I equal to 1 to n mod bi power q the whole power 1 by q less than or equal to xj by p plus yj by q for all j equal to 1 to etc. n. So if we are adding all these inequalities and simplifying, we are getting the Holder's inequality. And while simplifying, we are using the result 1 by p plus 1 by q equal to 1. So in the Holder's inequality, instead of p and q, if you take the value as 2, then we are having the result summation I equal to 1 to n mod ai bi less than or equal to summation I equal to 1 to n mod ai square the whole power 1 by 2 into summation I equal to 1 to n mod bi square the whole power 1 by 2. This result is known as Cauchy-Schwarz inequality. Next we can see Minkowski's inequality. So remember, in Holder's inequality the terms are multiplied. In Minkowski inequality the terms are added. So summation I equal to 1 to n mod ai plus bi power p the whole power 1 by p less than or equal to summation I equal to 1 to n mod ai power p the whole power 1 by p plus summation I equal to 1 to n mod bi power p the whole power 1 by p. Similarly, in the Holder's inequality, ai and bi are real numbers. So the inequality is trivial if p equal to 1. If we take p equal to 1, there is no need to prove. The inequality will become trivial. If p greater than 1, then summation I equal to 1 to n mod ai power ai plus bi power p the whole power 1 by p less than or equal to summation I equal to 1 to n mod ai plus mod bi the whole power p the whole power 1 by p. We are using this triangular inequality. Next I am considering the summation I equal to 1 to n mod ai plus mod bi the whole power p. So this whole power p can be split up into two terms, whole power p minus 1 into whole power 1. And using the Holder's inequality and using the result 1 by p plus 1 by q equal to 1, we are deriving this result for Minkowski inequality. So we are using mainly the Holder's inequality result to prove the Minkowski inequality result. Thank you.